What is the specific problem that the proposed method, memory mosaics, aims to solve?
The specific problem that the proposed method, memory mosaics, aims to solve is to efficiently address prediction tasks by leveraging multiple associative memories that can store key-value pairs and retrieve values based on queried keys. Memory mosaics focus on breaking down the overall prediction task into smaller, more manageable sub-problems that can be independently memorized and then recombined as needed. The architecture aims to disentangle the prediction problem by training the network to efficiently use memory units to predict future values based on past observations. This approach allows for transparent and interpretable learning mechanisms compared to traditional transformers. Memory mosaics also aim to optimize the efficiency of memory units by redistributing the prediction work among available memory units and adjusting key extraction functions to compare current and past prediction contexts effectively. Ultimately, the goal is to create a model that not only memorizes information, but also understands how to combine and reassemble this information in various ways to make accurate predictions.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, memory mosaics, works by utilizing multiple associative memories that work together to perform a prediction task. The architecture consists of elementary memory units, each comprising an associative memory and a trainable feature extractor. The keys are computed based on past observations, while the values represent what the memory aims to predict in the future. The associative memory stores key-value pairs and retrieves values based on queried keys using Gaussian kernel smoothing. During training, the network is unrolled in time and gradients are back-propagated through the network. The training process aims to make each memory unit statistically efficient by tuning key extraction functions to compare current and past prediction contexts. The network is trained to predict future values by leveraging past observations efficiently. The predictive disentanglement principle guides the training process, breaking down the overall prediction task into smaller, more manageable sub-problems that can be recombined in various ways. This approach allows the network to memorize disentangled fragments of information and understand how they fit together. The memory mosaics architecture resembles transformers, but offers more transparency in understanding its internal mechanisms and decision-making processes.
What are the theoretical or practical benefits of using memory mosaics over existing alternatives?
The theoretical benefits of using memory mosaics over existing alternatives lie in their ability to disentangle and compose knowledge in a transparent and efficient manner. Memory mosaics break down the overall prediction task into smaller, independently memorized fragments, which can then be recombined as needed. This disentanglement principle allows for more efficient memorization and prediction, as each memory unit can focus on specific aspects of the task. Additionally, memory mosaics provide a clear understanding of what each memory unit memorizes through its value extraction functions, unlike other models like transformers, whose internal mechanisms are harder to decipher. Practically, memory mosaics offer engineering opportunities such as implementing limited storage contextual memories by evicting the least recently used entry, which can optimize memory usage. They can also be implemented using various techniques like fast transforms or locality-sensitive hashing mechanisms, potentially reducing computing requirements in artificial intelligence systems. Furthermore, memory mosaics have shown promising performance in language modeling tasks, matching or slightly outperforming transformers in certain scenarios. Their ability to handle out-of-distribution tasks, such as predicting simple English Wikipedia articles, showcases their robustness and adaptability. Overall, memory mosaics offer a more interpretable and efficient approach to memory-based learning systems, making them a compelling choice for various applications in machine learning and artificial intelligence.
How were the networks of memory mosaics validated or tested in the experiments?
The networks of memory mosaics were validated and tested in the experiments by training them on the TINYSTORIES dataset and the BABISTORIES corpus, which contains stories written in a simple language. The training and validation curves of both transformers and memory mosaics of different depths were compared. The models were evaluated based on their ability to predict the next token in the input sequences. Additionally, the quality of the text generated by the models was compared using 24 prompts that tested the factual, logical, and consistency properties of the generated continuations. Furthermore, the models were evaluated on out-of-distribution tasks by predicting simple English Wikipedia articles, which were more sophisticated than the stories in the BABISTORIES corpus. The in-context learning abilities of the architectures were rigorously compared using the REGBENCH benchmark, which constructed artificial languages defined by probabilistic finite automatons. The memory mosaics outperformed transformers, recurrent neural networks, and state space models on this benchmark, showcasing their superior performance in learning and predicting sequences.
What results were achieved with the memory mosaics on the language modeling task?
The results achieved with memory mosaics on the language modeling task showed that they were able to handle language modeling tasks comparably to decoding transformers. The memory mosaics architecture closely matched the classic GPT-2 small transformer architecture in terms of performance. The training and validation curves of both transformers and memory mosaics of different depths, trained on the BABISTORIES dataset, indicated that the memory mosaic slightly outperformed the transformer for small depth networks, but this advantage disappeared as the depth increased. The qualitative evaluation of text generated by models trained on tiny stories showed that both the transformer and memory mosaic performed very similarly on tasks that tested factual, logical, and consistency properties of the generated continuations. Additionally, the out-of-distribution evaluation on the simple English Wikipedia articles demonstrated that memory mosaics substantially outperformed transformers after about 50 tokens, indicating superior in-context learning abilities. Furthermore, the memory mosaics dominated the REGBENCH benchmark, outperforming transformers, recurrent neural networks, and state space models for training set sizes covering 3 orders of magnitude. These results highlight the effectiveness and potential of memory mosaics in handling language modeling tasks.
What are the limitations or drawbacks of using memory mosaics in practical scenarios?
The limitations or drawbacks of using memory mosaics in practical scenarios include the challenge of training the architecture, which can be quite challenging and resemble the XOR networks of the early times. Reliable convergence may require specific strategies, such as restricting linear operations or clipping the mean squared loss. Additionally, the training process may bias the network towards a disentangled solution, potentially limiting the flexibility of the model. Another limitation is the need for careful design and tuning of the architecture, as hyperparameters that are optimized for transformer architectures may not directly transfer to memory mosaics, putting them at a slight disadvantage in certain comparisons. Furthermore, the complexity of the network, especially when layered memories are involved, can make it difficult to interpret and understand the inner workings of the model. Lastly, the implementation of memory mosaics with associative memories using kernel smoothing may limit the scalability and efficiency of the architecture compared to other memory mechanisms like fast transforms or locality-sensitive hashing.